All right, in our first example, we're going to compare data sets displayed in dot plots. So in our example, Sawyer has narrowed his car search down to two different types of cars. To make an informed decision, he gathers data on estimated highway fuel efficiency in miles per gallon of the two different types of cars. The dot plots show the data for each type. So what this is showing is how many miles each car can get per gallon in miles per gallon. So the two dot plots we can see visually look different. In type 1, we see there's kind of a cluster between, 33 and 38, 34, 35, 36, a little bit higher. A bit of an outlier here at 41. So this car at 41 gets more miles per gallon than these cars down here. So that's what that is saying. In type 2, you can see that the data is a little bit higher. We're not clustered in lower miles per gallon. We've got an outlier up here at 51. So these cars in general are going to get more miles per gallon when driving on the highway. So the first question, if highway fuel efficiency is the most important feature to Sawyer, which type of car should Sawyer purchase? So based on that, he should purchase the type 2 vehicle that he researched. We can see that the miles per gallon is a little bit higher than what the type 1 cars are getting while driving on the highway. All right, so we just concluded that based on the dot plots, Sawyer should buy a type 2 car. But Sawyer wants more information about the fuel efficiency of each type of car, so he calculates the mean and the mean absolute deviation, that MAD, that we had in our vocab of the two data sets. How can these measures help him make a more informed decision? All right, so here is some of the work to calculate a mean absolute deviation, the MAD, and this is just for the type 1 cars. Something I want to point out is that there are 16 total data points. And you can see that there are not, oops, there are not 16 data points listed. So what you can do to be a little bit more efficient is you don't have to create your little table to calculate a MAD score or a MAD value. You don't have to write your repeats. So for example, the data point of 33, over here it says occurrences, there were two 33s in your type 1 cars. There were three 34s. So we wrote it once, 34, and we're just taking note over here that there are three of those. There was only one 41 in that dot plot. There were three 36s. So you can just put your data points down and you don't have to write the repeats, and we will take note of the occurrences, how many of those were actually in the data set. All right, so to calculate the mean absolute deviation, calculate the absolute value of the difference between each data point and the mean. So first you do need to calculate the mean, and that was given to us right here. The mean for the type 1 cars is 35.75. So if we added up all the data points divided by the 16 total, we got a 35.75. So our second column, deviation from the mean, that is that difference between each data point and the mean. You can see we're taking 33, the data point, and we're subtracting the mean. We got 2.75. So that's how close is 33 to the mean, is 2.75 units away. It is the absolute value. When you do that subtraction, we just want it to be positive. Notice all of these differences are positive. Then how far away is 34 from the mean? So we subtract it, positive 1.75. How far away is 35 from the mean? Subtract it from the mean, or 35 minus the mean gets us a 0.75. So that's all we're doing, is we're taking each data point, we're subtracting the mean from it, and that tells us how far away each one is from the mean. Okay, what we're going to do next is we're going to find the mean of those differences. What is the average of these differences? So we have to take into account the occurrences. We didn't do this math 16 times for each data point. We just did it for each one, um, for each separate one, and then we'll account for the repeats right now. So what we do, if we had a difference of 2.75 when we had a data point of 33, that happened 2 times. So we're going to take 2 times that 2.75. Again, this just saves us some work, so we don't have to calculate that twice. We're going to add to that this 1.75. There were 3 occurrences of that, so 3 times 1.75 plus this difference 0.75 happened 3 times. So 3 times 0.75 plus 0.5, excuse me, 0.25 times 3 plus this 1.25 times 2. Oh, I kind of wrote that in a backwards order. It doesn't matter the order that you write these. Multiplication is commutative, so, if you like to do your multiplication in the other order, we'll get the same answer. This 2.25, we have 2 of those, so 2 times that 2.25 difference, plus last one, that 5.25 only occurred once, so I'm just going to say plus a 5.25. When we add all of those together, we get 26. Now we're going to divide that number by the data points to find our mean absolute deviation. So we take 26. Remember, there are 16 total data points, so we divide that by 16. And we're going to do a little rounding. It's about equal to a 1.63. So the type 1 cars has a mean absolute deviation of 1.63. What that means is on average, the data points are 1.63 units away from the mean. Okay, so use a similar process to find the mean absolute deviation of type 2 cars. Well, someone already did it for us. Here is that information. The mean absolute deviation of type 2 cars is about 2.94. So notice type 2 has a MAD, mean absolute deviation of 2.94. Type 1 has a smaller one of 1.63. So what do these measures mean about the fuel efficiency of type 1 versus type 2 cars? So remember, we said he should buy a type 2 car because from the dot plot, it looked like the type 2 cars had the higher highway fuel efficiency, and that's what was important to Sawyer. But upon closer look, here's what we noticed. Type 2 cars have a MAD, mean absolute deviation, of 2.94, which is higher than the MAD for the type 1 cars. So what that means is there is more variation with type 2 cars. Which could mean that the expected fuel efficiency is less reliable for type 2 cars. So when you have a higher MAD value, your data is more spread out, there is more variation, and it becomes a less reliable statistic to use about your data set. All right, so last question. How does the outlier in the second data set affect the mean and the MAD, the mean absolute deviation? So if we look at the data set, type 2 had a more extreme outlier. This 51 was significantly higher than the other ones. This 41, I said it was a bit of an outlier. It's just a little bit higher. So hopefully we can see that 51 is a true outlier. And we could calculate all this again. I won't take time for that in this video, but I just want you to know how an outlier will affect a mean and the mean absolute deviation, because that's another average of something. Any outlier will raise or lower a mean or a mean absolute deviation. How do you know if it's going to raise it or lower it? Well, if it's a higher outlier, it's going to raise it. If it's an outlier on the lower end, it will lower the mean. So it does pull that mean to higher or lower values depending on where the outlier is. So because the outlier was a higher number in the second data set, it will absolutely raise the mean and the mean absolute deviation.